Hello again, Calc students. This is Mrs. D picking up where she left off after having a technical difficulty. Never push the stop button. So we found the first area here in yellow, and we did that by hand. The rest of this I'm going to also do by hand, but I'm just going to pause. This first area we found is only for part of it. It's not even half of it, because notice this yellow region has a visibly smaller area than the next region in blue. To find that region, notice how the sine wave is on top now. So we're going to take and evaluate the difference between the sine function and the cosine function in this order. Now, if there's a question in your mind about why we're doing that, let me try to show you. Imagine all these points on this curve being subtracted. So those outputs, however high that is, we're going to subtract that number from this number on the cosine wave. We're going to subtract this number from that one on the cosine wave. If you continue to find all these differences, even when they're negative, you're creating kind of the length of a rectangle. And each of these rectangles has a very, very minute thickness. That thickness, if we go back to Riemann sums, which is kind of what we're doing here, that thickness is so thin. I don't even know why I'm calling it thickness. But here to here, here to here, all of these little widths, if you want to call them that, length and width of a rectangle, that is really that change in x, or that dx in the integral setup. So if you continue with this setup from pi over 4 to where we're ending, which is here at pi, then you'll get the other part of the area and we'll combine them. So evaluating this integral, we will be getting a larger value. We will be getting 1 plus, the double negative there will be plus the square root of 2 square units. So all in all then, putting these two areas together, we have a total area of 2 square roots of 2 square units. If we want to be exact, if we're going to round and be approximate, we should go to 3 decimal places and call this about 2.828 square units. So these are our final answers right here, whichever way you choose to write it. And in your practice, I would highly recommend that you do some of these problems by hand and some of them with your calculator, practicing that that calculator setup, finite integral, and work that out. Do all of your practice kind of in a mixed way. Don't do it all one way. Practice with a calculator, practice without a calculator. Now for our last example, this one's going to be probably most challenging to set up. And when I say set up, I mean like visually looking at the graph of this function, these functions, and actually one of them isn't a function. Notice that we have functions of y and functions of x. We're probably more comfortable with functions of x, but maybe take a moment and pause the video. Try to sketch the two curves and see how they relate to one another. Did you pause it? Really, give it a try. Okay, if you solve this equation for y, and you're trying to work in your comfort zone by getting it to be a function of x, and you might make a mistake here by plotting it just like this. So this is not exactly the same as what you've rewritten. I want you to get a little bit more comfortable with functions of y. So functions of x, we're comfortable when it's x squared, it's opening up. Parabola, if it's negative x squared, it opens down. We can think similarly with y squared. So y squared will open to the positive direction, and that's how this one's supposed to look. Parabola opening to the right. Negative y squared would open to the left. So we do have both the top and the bottom of this thing. Opening to the right, and notice it's shifted to the left 3 units. Not down, but left 3 units. So that's a horizontal shift. You kind of got to change your thinking to the horizontal axis. Now this line will intersect with this parabola and graphing a line. I'm sure you're comfortable with that. And we have 2 intersection points, and those will be important as we try to find this region. Take a moment, if you would, to try to find the intersection points. You can use substitution. You could use a graphing utility, I guess, if you want. Alright, so we're back. Did you find this intersection to be when y is equal to 2? And did you find this intersection to be when y is equal to 1? And all I'm worried about right now is, negative 1. It's the y values, because I'm going to set up this integral with respect to y, because I'm going to try to find all these little rectangles and their thickness as I go left to right here is going to be a little change in y. So this setup, and you'll have to do some like this. They're not really so easily done with x. We're using y, negative 1 to 2. Now here we're going to start with the more positive, so the one on the right, the difference between that and the one on the left will guarantee that we always get a positive area. So again, looking at the difference between the functions. So I'm going to rewrite this linear function as a function of y. It will say x equals y minus 1. Now what you can do with this one is worry about your setup and then use your calculator to evaluate. That's what I'm going to do. And then y squared minus 3 is what we're taking the difference of. You can clean this up a little bit and simplify it if you like. So we would have y plus 2 minus y squared to get rid of the parentheses. Evaluating from negative 1 to 2 still, we should be getting 4.5 square units. Now, practice, like I said, with your calculator, practice without. Sometimes you'll use the variable y. Sometimes you'll use the variable x. It's probably most natural or intuitive to use x because of all the things that we've done so far, but we do need to become well versed in both variables. This is Mrs. D signing out.